is slightly retrospective about C++, and how it's kind of played out in my own career. I may tell, well, and tell a story about Yarn. I mean, I apologize to everyone for not being at the banquet last night. I assume there were some Yarn stories there, but I'll just tell one from the day I met Yarn. Not the, yeah, I guess it was the day we met. So he had invited me and Jeremy Seek, who was a grad student at the time, to come visit, give a talk about the Matrix template library that we were working on at give a talk at AT&T. And when the day was over, Yarna and Andrew Koenig took us out to dinner at this place called, is it the Stinking Rose? Is that right? Yeah. Which, if you haven't had the pleasure of going to a restaurant called the Stinking Rose, it features garlic in everything. Lots of garlic. So we had garlic roasted chicken, and then for dessert and after, we had garlic ice cream and garlic schnapps. And I think after 3 or 4 days, I managed to actually clear it out of my system. But ever since, I know there's this relationship in my mind, it's Pavlovian somehow, between garlic and C++. And I was actually looking for, it's hard to find garlic schnapps. I was actually looking for some online and trying to find one in a store. All the best I can do is find recipes on how to make your own. So maybe in the future, the next fest trip, make something that age for the next years. But what I want to talk about now is, I guess, my favorite little technique in C++, because in some sense it's the smallest little extension I know of. It's just, as you see, 4 lines, and that's if you deliberately add 2 character terms, it makes it 4 lines long. But yet it provides quite a bit of power to libraries that we want to use or provide certain features that C++ just in and of itself doesn't provide. Now, some of this, a lot of these techniques and our explanations and explorations in C++ came in my never-ending quest, I guess, to bring modern software practices and programming languages to the scientific computing community. When I was in grad school, did a lot of American algebra, discovered C++, discovered operator overloading, and I could write a vector class, and I could write a matrix class, and I could overload operator star, and I could write A times X, and compute a matrix vector product that way, instead of calling dgem, blah, 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 all those things. So I thought this was significant, important, spent a lot of time trying to evangelize the scientific computing community with this wonderful discovery, quote unquote, that I made. And I got a little pat on the head. He was told, that's cute, come back when you can show sufficient performance for these things. Because as we all know, Fortran has performance and C++ doesn't. So I went back, and then I discovered generic programming. I discovered the STL, and again found a system that could get all these wonderful abstractions, but now you could in fact have the performance that everyone expects. You could match Fortran performance. So again, I decided this was a significant bit of information, went out into the scientific computing community to try to evangelize it, and again, pat on the head, slightly grayer head this time, and was told, well, with C++, as you know, object-oriented programming is too slow, and okay, well maybe this isn't object-oriented programming exactly, but it's C++, which supports object-oriented programming, and object-oriented programming is too slow, and on and on. So, well, I don't know. It was a slower process than I would have liked, and of course brought a famous quote by Max Planck to mind, that new scientific truth is not trying by convincing its opponents, making them see the light, but rather because its opponents eventually, well, he said die, I'll say retire. Which I guess for professors is the same thing. But because it's only essentially dying, a new generation grows up and is familiar with it. And in some ways, I'm unfortunately kind of seeing this play out in scientific community and C++ libraries. There are some of the newer departments of scientific, the new codes are being developed in C++. For instance, one of the most, I think, ambitious and significant libraries being developed right now is a library called Trilinos, and led by Mike Carudo at Sandia National Labs. And it really is a very modern C++ based system, really, doing almost every phase of scientific computing on parallel supercomputing. So it's very nice, and I think, again, as new generations are coming along who are familiar with C++, some of these techniques and features of C++ will be adapted and embraced. And I think it just is, maybe give some props to Bjarne on all this. I mean, it's been, because it has been a long process, trying to get this language into use in the scientific computing community. I think Bjarne needs to be recognized for his continued support, advocacy, leadership for the language, and really kind of keeping a consistent and coherent view of what it should be, so that, as we are waiting for the revolution, the language will be up to speed when that happens. So anyway, so C++, as I mentioned in my abstract, I'm really thinking of C++ as not just a language, but in a lot of ways as a programming language system or an open programming language platform. It is true that it's multi-paradigm, so it supports OO, supports C systems programming, supports generic programming. But in a lot of ways, because of some of the deliberate features that were put into C++, it is also extensible in new ways. And sometimes these features or this ability to extend C++ is called accidental. And I think that's a very unfortunate way of characterizing these things. It is true that some of these features that were developed, say by using template metaprogramming techniques, weren't originally developed as part of the template system, but the flexibility of the template system itself were deliberately designed to enable these kinds of things to be done. So I kind of bristle when people say, oh, it was an accident. It wasn't an accident. And there are systems like the Office library, concept checking library, main argument library, spirit parser, et cetera, that were built using some of the flexibility of C++ to create, in essence, new languages or extended versions of C++. Some of these, such as Lambda, moved from being just a library into new language. Concepts, well, almost became a language feature. Some more experience, I think, embedding some of the feature, some of the aspects of the feature to be performed before it moves from being library and so forth into an actual language feature. Hopefully in the next round, we'll be able to have that. So I just wanted to, again, briefly go through history of one technique. This came about when we were working on second or third or fourth, some iteration of our matrix template library, and we wanted to address some concerns about performance and optimization and so forth by, in essence, encoding optimizations within the library itself. And we, in fact, wanted to encode optimizations within the expression template libraries we were using with matrix template library. So we would be able to write A times X, and then depending on what the type of A was, and what the access patterns it had, and so forth. The correct multiply operation would be dispatched to, or actually be generated on the fly. It would be optimal for various, depending on some of the properties of those types were. It actually turned out to be a very interesting system. It did have one difficulty that does come up sometimes with template meta programs. I think we've got a 19 megabyte error message. But you have an optimized compiler as a type, right? So you make a mistake. So that's our current record that we know of anyway for an error message. But what we want to do, as I mentioned, we want to be able to do these and do it in, or we have the right to optimize or optimizable operators and do it in an extensible way. We'd like to be able to introduce new types. Of course, one of the extended library as this standard template library must be extensible with user types, and still have the user types able to take advantage of the operators and the optimizations. So in just using the typical expression template mechanism, for people who use that, plus operator plus, and all binary operators are overloaded to create a new type. You can essentially build a parse tree at compile time, or at runtime rather, and then the quality and so forth classes it and forces it to evaluate. But just the basic expression can provide all the functionality we wanted. Of course, one could specialize expression templates for specific library classes, but again, it's not as extensible, and we run into the common tutorial explosion because we have to write specialized versions for each pair of types. We looked at the Barton enactment trick, or what's called the curiously recurring template pattern, where operators can be defined generically. Again, this wasn't quite what we wanted because it becomes intrusive in the sense that mixing different libraries together requires mixing in essentially the Barton enactment trick. So this is where a very important feature of C++ came in. So this is it's called STINI, I think is the correct pronunciation. Stands for substitution failure is not an error. And this just has to do, it's a very perfectly sensible feature when one is looking through potential matches of a function, overload matches for a function. You need to try plugging in different types and generate the template, the function template, try to compile with that type substituted. But STINI means that rather than generating an error if the type and the template don't go together, they don't go together, it's just ignored. So we take that particular combination out as a candidate for an overload set. And so this allows, among other things, allows us to mix or have overloads of template functions versus with non-template functions. So try this idea. This seems to have been simultaneously invented in a couple of different places. Besides my group, Jaco and Jeremy Wilcock, Howard Knott is also working on this, and Paul Vincent and Jason Shirk had also contributed.
I think Richard Smith was one guy.
Yeah, I think he had a news group post early on also. This is in the 2002, 2003 time frame. This is the code for enable if. So it consists of one template, or full template structure, enable if, that has two arguments, a condition and an actual type, and then it has a specialization that specializes to the case of false, that has an Well, we notice that the difference between the fully general template and the specialized one is the body of the template itself just has a type def. It renames the template parameter T to type, and then in the specialized false case, we don't have that missing type number. So that's actually the SINI condition. So we have substitution failure on false.
Quick question? Just to clarify, those are the 4 lines of code you mentioned earlier?
Those are the 4 lines. And it seems very, okay, not remarkable. Let's see what we can do. Well, so if you use enable if in a function template signature, either as an extra argument that the function wouldn't have, or as part of the return type. So in this case, F, function template is templated on T, and now we use enable if and check to make sure that this type T has a certain trait. If it does not have that trait, that value will go to false. We get the second definition of enable if. Right? So the SINI will fail because there's no type def there, and then that function will be taken out of the possible overload set. So, and another way of doing it is again put enable if in the argument list and give it a default value. But typically, I think in most use cases I've seen it is with the return time. So some you can use it with classes as well. You want a certain class to be present or not. So then it goes out of for class template partialization, specialization. So another, or one feature, I guess, of this being able to pull functions in and out your user control in and out of the overload set is you can overload for specialized functions without having to do the tag dispatching that we've seen. So in STL, for instance, this is the advanced function. It's actually specialized depending on if you have a random access iterator, right, you can advance in order one time, in constant time, from where your iterator is to where you want to go, just by adding in to the iterator. For iterators that aren't random access, you have to go through a loop and add or increment the iterator one at a time. So it's important to be able to do that specialization for random access iterators. The way the specialization is done in the STL is each iterator has a tag, trace mechanism, accesses that, and then there is another function, underscore advance, has the tag as the third argument, and has overloaded that, and so the compiler will dispatch to the appropriate one with the function enabler version of the enable if version of dispatching. We can instead enable advance. You know, don't need this underscore advance. We can just call the random access version or the non-random access version by checking if the iterator is a random access iterator or not, and the appropriate one would be in the overload set for that type of iterator. Now the enable if, or this technique in some senses is more than just, it seems like a simple trick, right? So we have this whole line, you can put functions in and out of the overload set. In some sense, this is what I meant when talking about C++ being an extensible programming language platform, right? There's substance pieces of the compiler functionality of the overload resolution mechanisms that can be manipulated by source code programs. And there are other places where similar kind of things can be done with C++. This gives us the ability, subjects to extend and build the compiler to try out new features without having to be compiler hackers, and it lets one do it across different types of compilers, or different vendor compilers. So one of the features, of course, we've been interested in for some time is concepts, and I discussed those previously in his talk. So let's go through some of these. In some senses, like I mentioned, a concept is defined by a set of properties that a type might have. But with enable if, in some sense, we are able to invoke functions or not based on whether certain properties appear in the type that we pass into enable if. So in other words, we can overload functions, if you like, based on concepts rather than on particular type. So we can do concept-based overload, if you like. So this example, we have a print function, and we want to have it work for show types that model the showable concept. So not just particular types, but an entire class of types. And so using enable if, we have a traits class that determines whether a particular type conforms to the showable concept or not. And if it does, we invoke this particular version of print. And we can do other types of specializations with enable if. This example just shows one way of ameliorating some of the benefits or some unexpected behavior, let's say, of argument-dependent lookup. So if we want to make sure a specific version of spot in a particular namespace is called, again, we can use enable if to make sure we dispatch that one rather than we have to run across as we're going through the overload sets as determined by ADO. So anyway, this quick tour through some of the benefits of this particular small feature. The feature itself became a component in Boost, and I saw at least one code snippet that had std : enable if. So it's
I was very close.
Yeah, it's in C++ a lot.
okay, so it is actually part of the language, in fact. There's some neighbors as well. So conclusions, again, C++, I really consider it, it's been very important, as I mentioned in my own career, to be able to use some of this flexibility and power. I thank Bjarne sincerely for developing and advocating to continue to hold together this language and this community. Besides the simple thing of there's 4 different kinds of features that can be and have been prototyped and used in C++ libraries and then moved to language features. And so I think this and some of maybe of its other features will continue to keep C++ as a relevant and important language. And then my final conclusion is be prepared if Bjarne chooses a restaurant.
I was asking if advance or done with the enable it. Issues on it. Enable is remarkably neat and fun when you first get it, and then you use it in far too many places, and now trying to figure out when it's appropriate to use. So I come to something like this, and I wonder, how do I document this for the end user? I don't want to document it in the enable it form, because that's a lot of noise about the signature that the users need to see. But that's what appears in the header file. How am I documenting? What is the actual advanced function that the user should be thinking about?
That's a good point. So I think in that case, just template class iterator, class just in advance, kind of hide the as far as what the user would see.
So one thing I wonder, with enable if becoming so popular and the ugliness of the syntax, the fact that you often have to be clever of how to use it. In fact, it's really hard if there's not a return type to do it right. So what should the syntax be? We have this discussion about, say, the static if, or stuff that are doing resolving, which basically embeds the enable if technology in what looks like concepts. So you random iterator, IC, expand to that inside the compiler. We have been thoughts about how to get just the right semantics and some syntax that people can live with. This stuff's great, but it's hard to scale to meanings.
Right. Well, I thought 4 lines, even if it's obscure, it's easy to understand. No, I think as you mentioned, I think those things are still under discussion with static if. Might be more promising. At least it makes the syntax a little less, or a little more familiar.
Okay. I guess if people are willing to sprinkle these kind of things all over the standard library and elsewhere, it's a sign of we really want concept.
I think that's what it is.
So, I actually think these last two talks go together because I don't think you can reasonably say just ignore the enable if clauses when you're documenting this because the pragmatic effects of what kind of iterator you have, or even if you have an iterator, is important in how you use this type. So they don't have to see the syntax in the documentation, but they do have to know that being an iterator is required, and being a random access iterator changes the complexity.
Yeah. Well, again, this is the documentation, just having in this particular case, having concepts, and you could make that part of the interface of the document. In the right way.
My brief way of saying this is your order will be on concepts. And the concept is expressed as predicates, and the mechanism of producing items will be enable if. And we have to get back and actually talk about what it really is, rather than the implementation of it. But I think for the documentation, you can do exactly the first thing. This is order we're going to be, this is iterator.
Fun little anecdote. I was looking at argument, some old emails from argument at the time we were working on this. So he was very happy after working on the MetaWorks library and applied enable it to deal with some of the peculiarities of the type parsings in C++, and he had to implement the sign and cosine and hand functions and so forth. And he described a case where he managed to coalesce 730 overloads into 2 or 3. And he said there was a 2,000 overload set that he hadn't yet implemented, 2,000 function overload set to get all the conversions right. Now, for that, we had just given up, but we could do that in a few functions.
So that's one more question, which is the other problem I've had with enable it is if I've got get, if I'm at the function, I'd get a nice error to send me, okay, I've got to translate this half page, 3 page error with them to figure out why my type's not working quite right. If all I've got is an ambiguity, because I didn't catch any of them, and then the file, sorry, but I heard the file saying, here's a bunch of close things, I'm finding it's very hard to actually figure out why I didn't get the function I thought I was going to get. Have you had any luck in helping to figure a way through these kinds of diagnostics? Or is that still very much a research project or a towards concept?
I think that's definitely going to the context in our work on this.
I guess I'm going to do last resort, function that matches just the last resort. Just dot, dot, dot. Is Yuri going to do that? Yeah.
Usually like what, I use a lot of language and I like it for, and usually it's very good when the condition is kind of orthogonal to everything else. But like once you have an overload set where you have multiple conditions, you have to like pay attention that you always get exactly one coming out. Do you have any thought about how to improve it so that that's where I then start to create overload resolution because it doesn't have the problem. It usually chooses one, right? Have you thought about it? Can enable it to be like generalized or whatever the reincarnation of enabling will be the concept to avoid that problem that the conditions have to be exclusive?
Well, so sometimes we are recommended a disabled def, right? So that you can take things out to reduce ambiguity, or I guess we could have an enabled if and only if. At least kind of staying close particular techniques for resolving the ambiguity. Again, hopefully, as concepts continue to be developed, those kind of